Welcome, my dear students. In the last class, we discussed about the two theorems related to the linear transformation. In this class, we discuss some more results on the linear transformation. Last class, we prove one result where we can say that this result, where V and W be subspaces, and T from V to W be a linear transformation, and V1, V2, Vn be a vectors in a vector space V, such that V can be written as a linear combination of these vectors alpha 1, alpha 2, alpha n, where alpha 1, alpha 2, alpha n are scalars. Then TV can be written in the form of a this T can be written TV1, V2 and a linear combination of this form. Okay, because we have given as a T is a linear map. I already proved this proposition into the last class. Proof is very trivial because we have given into this form, and if we take this can write in the form of TV, we apply the T into the linear transformation. Whether this be T of V can be written in the form of a T times of you have a alpha 1 V1 plus so on alpha n and Vn, and because we have a given T is be a linear map, and T is a linear map means we have to take a T of alpha 1 V1 plus so on plus T of alpha n Vn, and also again use the linearity of a T. We can say that this can be written as a alpha 1 T of V1 and so on plus alpha n T of Vn. So this is the very trivial proof is there. We have to already prove this into the last lecture. This lecture we have to start with this lemma. I already explained you this lemma also in the last class. But I just prove this. We can suggest that V is a span of V1, V2, Vn. Now if V is the span of a V1, V2, Vn, that means this any arbitrary vector V belongs to the V, and V is nothing but is equal to you have a span of V1, V2 up to Vn. So this means we can say that this V can be written as a linear combination of these elements. So this can be written as alpha 1 V1 plus alpha 2 V2 and so on plus alpha n Vn, and by the T and V are the two linear transformations. So we can just say that T of V can be written in the form of a T of alpha 1 V1 plus alpha 2 V2 plus so on is alpha n Vn, and by the previous result this can be written in the T alpha 1 T of V1 plus, if V can be written in this form, T of V can be written in the form of alpha 2 T of V2 plus so on alpha n T of Vn, and we have a given also the condition is we have a given T of Vi is equal to S of Vi. This implies that you have a given is a T of V1 is the same as S of V1, and also we have a T of V2 is equal to S of V2, and in the similar fashion we go to we can say that T of Vn is equal to S of Tn, and this means this can be written in the form of alpha of S of V1 plus so on alpha to S of V2 plus so on plus alpha and S of Vn. Okay, so then again because S is giving a linear, this can be written as S of you have a alpha 1 V1 plus S of alpha 2 V2 plus so on S of alpha and Vn by the linearity of S. Again S is linear, so again use the additivity conditions alpha 1 V1 plus so on alpha 2 V2 plus so on alpha and Vn, and now this alpha 1 V1 V2 Vn we have a is equal to V, so this can be written as S of V, and V we have to choose an arbitrary element of a vector space V. So this was true for each and every V. T of V is equal to S of V for all V. That means we can say that S is equal to S is equal to T or T is equal to S. This is the proof of this lemma. Okay, we just took it like this. We take a arbitrary element, and since T of Vi is equal to, you have a S of Vi for I, previous propositions, if T of V can be written into by the proposition, this can be written in this form, and then we have to write because of a T of we have a given condition is like this, T of Vi is equal to S of Vi, I running 1 to n. So by this property we can write into this form, and T of V2 can be written into this form, and so on. And by again we use the linearity of S. So this can be written in the form of we have a right in the form alpha 1. This can be written as a S times of alpha 1 V1 plus S times of alpha 2 V2, and so on. S times of you have a S times of alpha and Vn. Again use the linearity of S, then we can write into this form. Now this is nothing but is equal to, you have a, this is completely we have to assume this is the vector V. So this is nothing but is equal to, you can say that simply is equal to S of V, because V is an arbitrary in a V, and this shows that T is equal to S into this. So we complete the proof of this theorem. Okay, now we have to move to the one more important result for this. Let V be a vector space with V1, V2, this is comma, V1, V2, Vn be a basis. This is means we have to take a basis. So this means these vectors we have to take in the form of a V1, V2 up to Vn is basis, means we have a two things is there. This should be a linearly independent, and span of these vectors V1, V2 up to Vn is equal to V. And W be another vector space, and W1, W2, Wn be an arbitrary vectors in W. So we have to choosing these n arbitrary vectors in W. And there is only one and only one linear transformation, this T of V, such that T of W is equal to T of Vi is equal to W of I. So this means there is a unique linear transformation can be exist where T of Ui is equal to W of I is zero. So this means we can just say that this can find a linear transformation which is be unique. So this means we can just start with the we have a V1, V2, Vn be a basis. So basis means we have any vector V where it belongs to the V. There are a unique scalars alpha 1, alpha 2, alpha n, such that V can be written into the form of this form. Now we first show that this representation is a unique. So we just assuming that we can also write in the form of a beta 1 V1 plus beta 2 V2 and so on, plus beta and Vn, and where beta 1, beta 2, beta n are the scalars. So we have all this beta is so beta 1, beta 2 up to beta n, these are scalars. Now because this is a unique representation for unique alpha 1 alpha, this is also V. So we can also write in the form of this, means we can write in alpha 1 V1 plus alpha 2 V2 and so on, plus alpha and Vn is the same as we have a beta 1 V1, beta 2 V2 and so on. We have a beta and Vn, and this can be written in the form of a, we have to write in the form of alpha 1 V1 plus alpha 2 V2 and so on, plus alpha and Vn plus minus beta 1 V1 plus minus beta 2 V2 and plus so on minus beta n Vn is equal to 0 vector. So we have to just now we have to combine the vectors V1, V2, Vn. So this can be written as alpha 1, and then we have a minus ka beta 1, we have a V1 plus we have a alpha 2 minus ka beta 2, we have a V2, and so on. We have to go up to the alpha n minus beta n Vn is equal to 0 vector. Now we have a given condition is this V1, V2, Vn is a basis. Means if it is basis, means this set of vectors are linearly independent. if this v1, v2, vn is linearly independent, means we can say that their scalar should be 0. So this implies that we can say that alpha 1 minus beta 1 is equal to 0. We have alpha 2 minus beta 2 is equal to 0, and so on. We can say that alpha n, we have to just in the same fashion we can say that alpha n minus beta n is equal to 0. So now we can just say that into this form, if we have a alpha 1 minus beta 1 is equal to 0, implies that alpha 1 is equal to beta 1. Similarly, we have a alpha 2 minus beta 2 is equal to 0, implies that alpha 2 is equal to beta 2, and similar fashion we can say that alpha n is equal to b times. So that means we can say that this, if we take a two different representation, scalars are unique, so we take a two different representation of this scalar, and then ultimately what we have to show that these two scalars are the same scalars. Okay, so we just say that v1, v2, we can representation v1 into this form and v2 representation into this form, beta suitable scalar, so v can be written into this form. So we uniquely is a unique representation. So we just write this alpha 1 v1, alpha 2 v2, alpha n vn is the same as a beta 1 v2 and beta 2 v2 and so on. So this means this can be written as a, we have to write in the form of a alpha 1 minus alpha 2 alpha 1 minus beta 1 v1 plus alpha 2 beta 2 v2 and so on, alpha n minus as beta and vn. But you know that we have a given v2, v1, v2 up to vn is linearly independent. So if these vectors are linearly independent, so we have these vectors are linearly independent, so corresponding scalar must be equal to 0. So we just say that alpha 1 minus beta 1 is equal to 0. So and this so on for each I, alpha I is equal to beta I. So we can say that this is clearly this expression v representation is a unique representation. Now next part we have to consider a mapping from T from V to W, and we have to just write T of V can be written into this form because you have a given V1, V2, Vn, we have a given is a basis, V1, V2 up to Vn is a basis of vector space V. If V1, V2, Vn is a basis, then V can be written as a finite linear combination of the elements of the vector space V. So now first we have to try to show that this representation TV from gamma 1 W1 plus gamma 2 W2 plus gamma n Wn is a linear. If it is showing the linear, that means we have to take a V and U are the two representation of a V, and then V can be written as a V is the element of a V and U also the element of a V. Then T of V is this form, we have a T of V is the form of you have a gamma 1 W1 plus so on gamma n Wn, and T of U we can represent as a delta 1 W1 plus so on, we have a delta n and Wn. So we just representation U in the form of this UV belongs to V, alpha is any scalar, and U is written in this form. We already know that V because V1, V2, Vn is a basis, so V can be also written as alpha 1 V1 plus so on alpha n Vn. This is we already this representation is unique, we already show that. Now we choose another vector which is not the same of as a V. So U can be also written as a linear combination of the vectors of this, where delta 1, delta 2 and delta n are scalars. So we have all this delta 1, delta 2, delta n are scalars. So we have to just say that V1 V is not equal to this condition, we have to impose it. Now we have to calculate the calculate the U plus V, and then U plus V means you have a alpha 1 V1 plus so on, we have a alpha n and Vn plus U is equal to we just write this is as a form of a V plus U, and then you have this is delta 1 V1 plus so on delta and Vn, and now by this can be written in the form of a similarly the alpha 1 plus delta 1 V1 plus so on, we have a alpha n plus delta n Vn. And now if we have to calculating this is equal to some t of u is this form, and then similarly t of u we have to choosing this form. So this means I just take a this form in place of v, because linearity we have to show that this time either we chose the u plus v is equal to tu plus t of v, and t of alpha of u plus alpha u is equal to alpha times t of u. So this I just try to prove combine these two. I take a should try to show that alpha times of we have a v plus u. This should be alpha times t of a v plus t of u in this form. So u is this form. So we have to calculate the alpha times of this alpha v plus u. So alpha times v is equal to, we have this term, and now this can be written as alpha 1 v1 plus you have to just show that alpha 2 v2 and so on, alpha n vn plus we have a delta 1 v1 plus so on delta n vn. Now this can be written as alpha 1 plus delta 1 v1, and then you have a plus alpha 2 plus delta 2 we have a v2 and so on, plus alpha n plus delta n vn. Okay, so now we just say that this way we can write into this form again, because you just say that you have to apply the t from this side. So this way we can write t of alpha applying the t. If we applying the t of alpha v plus u is equal to this form. Now this is nothing but is equal to t is you have a giving the linear. So this means if t is a linear, that means you can say that this linearity of a t, we can just say that this can be whole thing is t of this can be written as t of alpha 1 plus delta 1 v1, and then we have a plus t times of alpha 2 plus delta 2 v2 and so on, and this is nothing but equal to t of alpha n plus delta n we have a vn. And now again by the linearity, this can be written alpha 1 plus delta 1 we have a t of v1, and then we have a similarly we have a alpha n plus delta n t of vn. So this way we can write into a this by we take a linearity of this. First we apply the linearity of here, then again apply the linearity of a t is equal to this. And now because you have a this is nothing but equal to t of v1 is equal to you have a w1, t of v2 is equal to w2, and then so on. So this means this can be written in this form. So we have write into a this form. So now again we can write this is the alpha 1 w1 plus this and so on, this is equal to this, and now this is nothing but is equal to this can be written in the form of again w1 is equal to we have to write is a t1, and this is nothing but is equal to what we take a alpha we just take a alpha from this is equal to alpha times of alpha 1 w1 alpha 2 w2 plus alpha n wn plus you have a delta 1 w1 plus so on delta n wn, and this is nothing but alpha times this is nothing but is equal to you have a t of v plus d of a u, and then this can be we have to write into a this form. So this means t we have to write from v to t of alpha u alpha v u is equal to alpha times t of u plus t of v. So this means we can just say that this is alpha time t times of alpha v plus u is the same as a alpha times of a tv plus t of u. So this means the map we have to define t from this map we define clearly this t from v to v, where this is on the form of this t of v is equal to gamma 1 w1 plus gamma 2 w2. This is nothing but is equal to, you can say that this is nothing but t of v1 we can get gamma 1 or t of a image of a this is equal to, if we have arbitrary v, then this is nothing but is equal to element of a v is there. Okay, so now this is we have to show that this is a t is a linear. Now because by this condition, because since t of delta 1 this is equal to by using this property. So this is nothing but is equal to delta 1. So by this we can clearly say that the map defined tree from u to v to w by the map t of v is equal to gamma 1 w1 plus gamma 2 w2 plus gamma n wn is a linear map. Okay, so hence we have to show that this map we define is a linear. Now we have a v1, v2, vn, be an arbitrary vector v. Then v1 can be written in the form of 1 into v1 plus 0 into vn, because the property of a vector space 1 into v is equal to you have a v by this property. Similarly, we can write v2, t of v1 can be written in the form of a we have to write t of v1 can be written t of v1 can be written as a t of 1 into v1 plus so on 0 into vn by the linearity t of v1, and t of v1 is equal to you have a 1 into t of v1 and 1 into t of v1 is equal to w1 plus 0 into w2 and so on. So this means we can write t of v is equal to 1 is equal to this form. Similarly, t of v2 can be written as a 0 into because v2 can be written as a 0 into v1 plus 1 into v2 plus so on 0 into vn. Then again t of v2 can be written in the form of this. We have to, and this is nothing but is equal to you have a w1, this is nothing but is equal to you have a w2, and similarly you have a t of v3 can be written as a you can write as a 0 into v1 plus 0 into v2 plus 1 into v3 plus so on plus 0 into vn, and this can be written in the form of a this is nothing but is equal to we have to write sorry, this is we can write v3, and t of v3 can be written as 0 into t of v1 is equal to w1, 0 into t of v2 is equal to w2 plus 1 into t of v3 is equal to w3 and so on. We have a 0 into wn. So in the same fashion we have to go up to the n terms. So we just take a v of n is in the form of a this form. So this is nothing but is equal to w1, w2 and wn, and so we just say that t of vi is equal to wi for or each I running 1 to n. Now suppose this is, we have to show that this is the only transformation which gives representation t of vi is equal to wi. There does not exist any other transformation. So we consider another transformation maybe exists. Suppose S be another linear transformation such that S of v also satisfy this condition. So if this condition, then v is the element of a v, we have a v is the form of this form, and then we have to calculate S of v. S of v is nothing but is equal to, because S is a linear, alpha 1 we have a S of v1, alpha 2 S of v2 and so on plus alpha n S of vn, and alpha 1 S of v1 is equal to, by this condition, is equal to w1, and this is alpha 2 w2 and so on alpha n wn. So S of v can be representing into this form. So this means we can just say that, and also we have a t of this. So S of v can be written in this form. So this is the form of this. So we write into a this form. So alpha 1 w1, alpha 2 w2 and so on. So S of v can be representing into a this form. Okay, so this is nothing but is equal to, we have to this is also is a t of v, and we already proved the previous result where we have show that if t of vi is equal to S of vi for I running 1 to n, then we have to just say that t and s are the same, then t is equal to, you have a s in this form. So now again we have to just try for a rough sketching is this. So this means this implies that S is equal to this is true for all S v. This means we have to complete the proof of this theorem. So now we have to show this complete the proof of this theorem. That means if we have a t from v to w is a v is a basis, and w we have a v1 up to vn is a basis, and w1 we have a w1 w2 up to wn any vectors in w, then there is a unique representation of a T of Vi is equal to Wi. With this we can just say that by this property we can use by this property we can also representation find the general terms of the vector space. For example, if we take a suppose I take a basis B is equal to we take a 1 0 and 0 1. This is the basis, this is a standard basis for any vector space. This and V is equal to I take a T is a map from V2 to I just define it for R2 to R2 to R2, and we have to take a T of 1 0 is equal to we have for the moment we have a given vectors is equal to 1 and 2. T of 0 1 is equal to you have a suppose is equal to 2 and 1, and then we try to check is this map is a linear or not. And now you see this if we have given this because this is the basis, so we can find the general formula by this method. There exists a by this theorem is saying that T of Vi can be represented as Wi. So if we take x and y are the any arbitrary element of this R2, then R2 if arbitrary element of this R2, then this x and y can be written as a finite linear combination of the vectors of this. So x and y can be written as x times of a 1 0 plus you have a y times of a 0 1, and then you can say that this is T of x y can be representation x of T of 1 0 plus y times T of 0 1, and this can be written in the form of a x T of 1 0 we define as a 1 and 2 plus y times we define as a 2 and 1. So this can be written as a x plus 2y, and then you have a 2x plus y, and this is clearly you can just easily verify this set. This is a general formula for a vector space. So any if we have a basis vector and T is a linear map from V to W and W1 W2 any arbitrary vectors in a W, then T of Vi is always equal to Wi. We can represent this representation is a unique for all these things. So I just complete this theorem and also complete the by this example. I stop today's lecture here. In the next class we discuss some problems related to this linear transformation. How to we find a if we have a given some basis vector and we define a map t particular values, and how to define a general linear transformation map by applying this theorem. So thank you very much for this lecture. We continue for next class some examples based on this theorems whatever we have proved in this class. So thank you very much.